All right, so let's first go through the importance, organization, and goal of this mini-series. So the idea we had here was to start this mini-series as a periodical and regular event, was to share the knowledge across the community. Also, we intend to invite panelists at the later episode, have more open discussions, identify new challenges and the features that are required in the sphere of the Open RAN and ORAN, obviously. We would like also to support the acceleration of this R&D cycle from idea to the proof of concept prototype. So how we can actually bring an idea into the existence by rapidly being able to provide the proof of concept prototype. Also showing ideas and validate use cases. And finally, foster academic and industry collaboration, which I believe is very, very important. So I would like to start by highlighting the fact that currently 5G and 6G open source ecosystems are complex. Not that they are becoming complex, they are actually complex. So here I put a very simplified screenshot of different framework that exist with different researchers, different people, different engineers that are interested in different areas. And for instance, we see here, we have a lot of open source ecosystem for 5G, open air interface, SRS RAN on the RAN part, and also on the core part, again, open air interface, open 5GS, free 5GS. We have ORAN with the disaggregated architecture, with the RIC, with the SMO that also adds additional complexity when you actually go to the scale. Then you have a clouds like Kubernetes, public clouds, private clouds, and also a bunch of new frameworks that are emerging for the machine learning and AI, like Kubeflow, MLflow. MLflow is quite recent, that is pushed by Canonical Ubuntu, also edge application and so forth. So this makes the whole things very complex and not easy for everyone to be able to understand which framework is the best for the specific idea, for the specific proof of concept. So essentially what we observe here is that the open and free softwares are becoming expensive in a sense that, okay, actually there is no initial barrier to download the software. So the software cost is somewhat decreasing or sometimes fluctuating. But what makes it complex here is the operational cost and the time. And here on the right picture, I put you some of the facts that we have actually discovered through questionnaires, that essentially it's easy to set up a testbed at the beginning, but then to maintain it, to upgrade it, to add new use cases, to make sure that this platform has the stability that is required, the performance is quite complex. And we see here, we have different type of users. So we have at some point, at some level, we have professors and the students, they want to use this for the perspective of the learning, education, and let's say training. And then on the other side, we have researchers and the developers that they want to use the platform for the purpose of their R&D, their, let's say, research topics, proof of concept again, developing new ideas, and mixing different domains together, like an edge domain, core network domain, RAN domain, machine learning domain, all together into one platform that is actually useful for the purpose of the research and the development. Here we have an example testbed from NTUSD NYCU in Taiwan. So this is the actual testbed that it's used in Taiwan. So this testbed you see is quite complex. You have a bunch of, so you have a tester like a VIV, you have OAI, you have ORAN, you have Radisys. So some of them are commercials, some of them are open source. you have, let's say, Nokia Core Network, SA Box, Free 5GC, and FlexRig from OAI, and so forth. And this, you see that now the ecosystem is kind of multi-vendor, and later we are going to elaborate on multi-X, multi-vendor, and it is very interesting to be able to easily mix and match different software platforms. But at the same time, if this operation is manual, and if this operation is not a standard compliant, like if you are not using software like OEMs designed or specified by ORAN, for instance, that makes the whole operation very, very costly. Like when you want to update the picture that I showed to you before, so you always need quite a lot of effort for the upgrade, for deployment, for the operation, and so forth. And another thing you see on the right is that most of the testbed currently, when you run it, you only run, let's say, one single vendor at a time, or one combination at a time. So that is quite challenging today to be able, on the same infrastructure, deploy different combination of the vendors simultaneously, not at a time, which we refer to the multi-X here. Like you can on the fly mix and match different components of different vendors to build your testbed and do the experiment. And that is quite useful for understanding the system, for gathering the data, and providing, let's say, some validating some ideas in this ecosystem. So in OpenRAN Studio, what is OpenRAN Studio? OpenRAN Studio tries to actually solve this problem by providing an ecosystem that spans from learning, that use, for instance, in this case, a device which is more like a in a simulated, emulated environment, towards a deployment. The full life cycle for researchers or students that starts to learn the environment towards the actual deployment of that environment, and all with the same user interface and a consistent environment. So this is actually what we are trying to do with OpenRAN Studio. And what you see on the left here, that there are 3 ways that this could be actually used. It could be like a single node. You have a OpenRAN Studio in a box that makes you one, let's say, a specific individual environment. But also you can expand it towards the infrastructure, like on a private cloud, like locally on premises. You deploy the environment on your private infrastructure, or you deploy it on a public cloud. That is one of the topics we are going to cover today. We are going to show you how this environment could be deployed in a Google Cloud Engine. And we know that there are many different types of users. So like students, researchers, or even engineers. You have different scenarios. You have scenarios of let's say, using for the teaching, R&D, proof of concept, and deployment, and use cases, again, that Industry 4.0, train, media. So you have different type of usage and needs that must be met inside the same environment. So today, the global presence of OpenRAN Studio is quite positive. So you see, this is the map of the adoption, and more in universities and organizations are adopting. We are also offering the lab manuals, which we have episodes, a specific episode with the episode title. We provide some background resources, guided instruction, some basic and bonus questions, and then the report. And we have some testimony of those that they are actually using. And we're very happy to say that this platform is getting a growing adoption throughout internationally. So the final goal of OpenRAN Studio that we strive to do is to empower communities and organizations to accelerate the adoption of the modern technologies, like the state-of-the-art and also the cutting-edge technologies, solid ground for tutoring the next generation researchers and engineers. So we would like to have an environment where the researchers and the future engineers, they can actually use this as a starting point, and from learning towards a deployment, reproducible and verifiable and consistent outcome for teaching and research. So in research, there is a problem always since the beginning for reproducibility and verifiability of the outcome. And one of our objectives is to make sure that the research and the results that has been produced by one researcher could be reproduced by the other researchers. And this is actually realized throughout the platform. Also, we would like that this platform to be affordable and accessible means for education and research, and opening new possibilities and dimension via multidisciplinary research. So that means that we are combining edge cloud, data centers, AI, ML, data science, Open RAN, 5G, 6G, security, application, and that will open up in dimensions and possibilities for combining different domains together and do multidisciplinary research. So with that, I would like to go to the agenda and introduce the speakers today. So we have today two parts. Part one, we foresee 45 minutes. We start presenting the OpenRAN Studio features and the bronze release note. Then we demonstrate, we show you the open non-RT-RIC architecture and the RApp call flows. Then operation and management. Here we show you in a step-by-step manner how to design and deploy a 5G OpenRAN network on Google Kubernetes engine. So this essentially helps you to understand in a public cloud environment how this 5G OpenRAN could be deployed and could be used for the purpose of the learning and R&D. Then we make a break. Then we go to the part two, and in part two, we cover the xApp lifecycle from the developer perspective towards the production. We want to cover the whole spectrum for a developer's perspective. What does it mean xApp? And from the production and the deployment perspective, what does it mean the xApp? And we consider a RAN slicing use case here. Then we deploy a large scale 5G OpenRAN network in our private cloud here, which composed of, if I'm not mistaken, 14 GNodeB, and we perform some data analytics on the top. Then we go to a DevOps xApp, which is, we call it interactive xApp, that actually showing how to interact with the internals of the xApp, what are the steps in each xApp to be considered, and by the maintainers, by the developers. Then we go to the observability. We show how to process the data flow with the agility and on real time. Then we have a guest demo from NTUSD that shows interoperability between OpenRAN Studio and OSCDU. And finally, we have some closing remarks, and we go to the Q&A session. So the speakers here, we have Ali Reza from BubbleRAN and Ilyas from Eurocom. They are presenting the first part. And then on the second part, we have Chichen, Koa, and Yuan that are going to present the second part. So without further ado, we move to the actual event. I pass the ball to my colleagues, so they are going to continue the presentation. And feel free to, again, ask your questions in the chat. We will answer you very quickly.
Okay, hello everyone. I welcome on my behalf. I welcome you on my behalf to this webinar. Okay, before I start my presentation, since as Navid mentioned, we are going to do this demo on Google Cloud, the first half of the demo on Google Cloud, I would like to start running Google Cloud while it is allocating the resources for us. We go through the slides and then we come back to see how we can interact with it. So already you see I'm my Google dashboard and there's no cluster created. I go to my terminal and I try to create the resources. It will start creating the resource via Terraform, and then I go back to my presentation until this is finished. It would take roughly a few minutes, so to not waste the time, I go for presentation. Okay, so it's started creating. Let's start the presentation. All right, so as I was telling you about, the infrastructure that we're using for the first part of the demo is on Google Kubernetes Engine. And we are going to do, as we showed you, is automated cluster deployment in one command that I did from apply auto approve. And it would help us to have we start from infrastructure, we get access to Google Cloud, and then we reach to ORS service in a few minutes, say 10 minutes in this case. And this is a pay-as-you-go service with Google Cloud. So you pay for your infrastructure as long as you're using it. At the end of this demo, for example, we delete the resources and then there is no further cost incurred to us. And the deployment of this ORS, as we mentioned, we are using Terraform and Kubernetes Engine. There are other modes of installation that I would address later. So before that, we want to show like how ORS would look, how your interaction with ORS would look like in a nutshell. We recognize, say, 5 steps that you usually interact with ORS. First, you would like to think about design and development of your network. This is a first-time phenomenon, like say in simulation of the RAN networks and the core networks, is that you think about the design of the network as if you would see it normally as you hope. Sorry, as you describe the network yourself. Then you deploy your network and customize it as you wish. Then you can do measurements and tests end-to-end and analyze and evaluate your network that you just deployed. This is incorporating all the techniques from DevOps while being, so in that sense, OpenRAN Studio is the world's first production-grade cloud-native platform to seamlessly design, operate, experiment, say an emulated or simulated end-to-end TGPP and or an standard compliant network, plus edge services and at a scale. So we see the scale is a lot. We have covered parts of it in the last webinar. You could find the videos on YouTube or YouTube account of BubbleRAN. And we are trying to gradually cover more and more in each webinar episode. So just a couple of features that I want to mention about ORS that most of them we cover in this episode. As we said, there's the multi-infrastructure support. So we support bare metal deployments. We support on-premise or private clouds. You have public clouds. You have also the single node option that Navid mentioned via micro-KTS. We do have an ORAN compliant SMO and RIC stack, including non-RT, near-RT, and OAM. You have the network design, protocol tracing, log extraction, and as well as integrated UE testing. You have RApps and xApps, both for monitoring and control. You have the end-to-end agile and scalable declarative deployment, including the UE. This is like the fancy terms that we use in Cloud Sense, which allows you essentially to define your network as how you wish it to look like, not as the steps that you need to achieve that. We incorporate also day 2 features like network reconfiguration, upgrade, fault management. There is, as I mentioned earlier, there's a difference between declarative and imperative deployments that in the declarative one, you mention how you want your network look like, not what are the steps to achieve it, unlike the imperative one. We would see the examples of how you design and deploy the network later. We support multiple vendors, OI, SRS, Open5GS in both LTE and NL mode. We have programmable cloud native observability that we would see today, and as well as multi-source data lake, which includes RAN, energy, and infrastructure metrics. Elias, could you please, someone, I don't know how to remove this, someone annotated the slides. All right, so here we are going to focus on, thank you. We are focusing on ORS release 2. Bronze is the code name of it. This would be rolling out for the current customers who are using ORS already for starting this week, and the new customers would start receiving it from December. Then there are, as I mentioned, there are multiple installation options that you could choose. You could have pay-as-you-go with Google Cloud. You could have a smaller scale single node with micro-KTS, or remote installation that we perform for you for larger scale networks that we use Cube, ADM, and Cloud Init features. The use cases, some of them I have mentioned here as following up Navid's slide and presentation, which is like education and training, data collection, and model training, of course, to have ORAP, xApp design and analysis, interoperability testing, which we would see part of it in our guest demo today. Test and measurement with the UE in the loop. You have validation of your research results. You have network simulation and emulation. So that is the kind of use case that you foresee with OpenRAN Studio, or the shorthand ORS. But I need to mention that this ORS is the first step of a member of products that you could upgrade to, which are like ORS. The focus is more on these use cases and more on education and training. That's why it uses simulator and emulator mode. But there are extension of the software that allows you to run with actual radio over the air. That are the, say, more expensive products of BubbleRAN, which use the same criteria, the same platform. In that sense, if you're trained to use how to use ORS, you could easily upgrade your system to use other products, say MX-PDK or MX Pro, and you use them as it is. Okay, so I would like here to give the floor to one of my colleagues who is going to explain our revisit of ORAN ecosystem and how these ORAPs and xApps would look like. Before I give the floor, it is still deploying, so we would come back later for Google Cloud. So I give the floor to my colleague. I stop sharing.
So hello everyone from my side. So I will now share my screen. I guess that you can see my screen now. So now we will try to explain what is our view of the ORAN ecosystem. So we have two figures here. If we focus on the left part, we will see that here is the ORAN architecture. We have all the interfaces and all the components of the ORAN architecture. If we can see on the top, there is the SMO with a non-RT rig and the ARAPs onboarded. We have the near real-time rig that it is connected with the A1 interface, and the near real-time rig has the xApps. We can see that the E2 interface connects to the CU, the control plane and CU user plane. We have the CUs here, we have the DUs and the radio units and the O cloud, and there are all the interfaces around them, the O1 and the O2. And now we're gonna see on the right part how we realize this on our platform and what we believe is a good way to realize it in a cloud native environment. So we will start from the bottom part. So at the bottom part, as we can see, we have the 5G network. Let's start from the baseline. So here we have the core network connected to a disaggregated G-Node B. We have the CU, we have the DU, and we have one UE in the loop. So here we have the 5G network. And now ORAN comes into the game, and we have the near real-time rig controller, which is the FlexRig controller, which is for near real-time loop with the E2 interface. We have the xApp that are connected as an SDK. So FlexRig is an SDK that supports xApp development and facilitates xApp development for different use cases. And now we have the SMO part here, that the SMO part consists of two important entities. So we have the Athena operator and the Odin operator. The Athena operator is for the OAM, for the operation and management part, and it is for managing the network functions, the lifecycle, managing the fault tolerance, for example, and these kind of things. And Odin, on the other part, is our realization of non-real-time rig, which is more for run optimization, for control actions, for enforcing policies, enrichment, and machine learning model management. So Odin is more for the control part and is more about sending the policies, finding the appropriate xApps to control the run. And on top of the SMO and Odin of the non-real-time rig, we have several RApps that can enforce policies that are intent-based, maybe. So maybe the RApps are intent-based, and they enforce policies, they monitor the network, and they can bring a certain behavior that is desired. So this is the whole ecosystem, and maybe we can go now to see how a policy will be sent. So the policies that are coming from the RApps, we will see now the traffic flow, how these policies can be forwarded and sent from the RApps down to the run. So we can see that the RApp first creates the policy. So we realize the policy as a custom resource definition. It is a CRD on the Kubernetes API. So we send a policy, a specific policy, to the Odin. The Odin, the non-RT rig, will read, receive, and reconcile this policy. And then dynamically, it will find the appropriate dynamic xApp in order to deploy it. So this dynamic xApp here does not appear before the policy comes. So it's a dynamic xApp. It is coming on demand for the policy. So Odin, the non-RT rig, will pick and deploy this xApp and will wait. So when the xApp is deployed, it will open some APIs to receive the policies. And after this time, we can send the policies to the APIs from Odin. So Odin will send the policies, and the dynamic xApp will try to enforce the policy. So let's say now that another policy is coming. So at this moment, because there is the appropriate xApp already now running, the dynamic xApp is already running, we don't need to deploy it again. So Odin intelligently understands that we have a dynamic xApp already that can support this policy. So it just forwards through the APIs the policy to the dynamic xApp, and the xApp will try to enforce here again the policy. So now let's say that we want to delete the policy. We don't want anymore this policy to be enforced on the run. And now we will send the delete policy CRD. We will delete the policy CRD from the Kubernetes API, and Odin will reconcile again. The Odin controller will receive the request and reconcile and find the appropriate dynamic xApp and gracefully delete the xApp by unsubscribing from the near real-time rig, from the flex rig, and then deleting the dynamic xApp pod and everything gracefully. So this is the life cycle of the policy, from deploying the dynamic xApp, forwarding through the APIs, and deleting the xApp. And I think if the Google Cloud is ready, we can proceed. Is ready? Okay, so I give back the screen to my colleague Alireza to show that it is ready.
Okay, so the Terraform is finished now, and if I do, I need to export the kube config that it generated, and then I do CLI extract infra command, and it shows me the cloud that we just did. So you see, we used Europe West T2, Europe West 2 region, and there are 3 nodes that we reserved with these IP addresses that are private local IP addresses with Ubuntu 22 machines, and they were running roughly 8 CPU core on each of them and 30 gig of RAM on each. So now my colleague would use this, and he would download the credentials separately for himself and would apply it to his setup. And then he would show you step by step how to design a network and how to apply it in your cluster.
Okay. So here we have our terminals. Now we'll try to connect to the Google Cloud. So it is only 2 commands that we need to run. It is first we need to export the kubeconfig file, and then we need to connect to the cloud. So here we have the commands. Let's try now to connect to GCP. As we can see, we are connected now. So at this moment, in every terminal that we open, we need to export this kubeconfig in order to be sure that we are using the GCP cluster and not our local cluster. So we do this now to be sure. Okay. And now we see that with these 2 commands, very easily we get the config generated from Terraform, as my colleague Alireza showed earlier. And we manually download the config from Google Cloud and we put it inside the kubeconfig. And then we export the kubeconfig to every other terminal to use the Google Cloud. So now we will try to build from zero a network step by step. And we will try to bring the whole ecosystem into play. So as we can see here, we will deploy 4 steps. So the step 1 will only have the 5G network, the core network, the RAN without the UE. So here we see step 1 is with black. We have the core network, we have the RAN, we have the FlexRig and the Odin without the UE. And we will open the Wireshark in order for the later steps to see the message exchanges and the packets. As a step 2, we will try to connect the UE with just an upgrade on the network YAML file that we'll deploy, and we will do some throughput tests in order to see the traffic from the Pika files from Wireshark. So later, step 3 will be to deploy again with a simple upgrade. We will deploy an interactive xApp written in Go, and step 4 we will deploy 2 RApps, and the RApps will trigger some dynamic xApp that will enforce the policies coming from the RApps. So we'll do the test measurements, packet tracing, we'll show xApp and RApps and the UE in the loop. So let's go now to step 1. Step 1 is to have the 5G network. As we can see here, there is the core network, the RAN, and we already have the FlexRig, the near real-time rig, and the Odin, the non-real-time rig, connected and waiting to serve. So on the right path here, you can see how the network YAML file looks like when you want to deploy such a network. So you can see that it's a very easy and human readable language. You can you have the section for access network, the core and the edge. So on the access network, you specify that you want a monolithic G-Node B, OIRAN, 5G standalone stack, and you give the identity. The radio is RF simulator, and the cell, you specify the band and the details that you want for the cells. And you say specifically that we want the core network here to be this core network that we define in the core network section, OI core network, OI SIM, and the controller, that is the edge section, we want to be FlexRig OI SIM. So for the core, you see that it uses the model, the minimal model, and we have some identities. And for the edge, it is FlexRig 5G standalone Mosaic 5G from the composition models FlexRig. So we will do, in order to deploy this network, we do CLI install network. We use the CLI install network step 1 YAML, and then we will use the other commands to open the wireshark. So let's go now to the terminals. So here we have the commands. We can install the network, the step 1 here. And let's wait. We can see that the network is created. We can use the CLI observe now in order to see the elements. I think we can see the elements fine. So we can see now that we have deployed the FlexRig, the near real-time rig. We have the core network AMF DB database, SMF UPF, and we have also the RAN, the G0B, and they wait for the connection of the UE. Odin is also installed, but we don't see it here in these elements because this is for the elements. So now let's open the wireshark. Yes. So you can talk if you want. Alireza, my colleague, wants to add something.
So there is one thing that I want to mention about the image that we showed, the YAML file. That YAML file is just a portion of the YAML file that you give actually at the end. The actual YAML file is longer, like it has the other sections to it. That's why you see when you say OIC and that OIC, it is because the file is cropped and the whole network name was called OIC. That's why I just wanted to add that this is a cropped version of the total file that you give to it. Okay, thank you.
Okay, thank you. Yes, this is a part of the network YAML file, and we deployed now the step 1. So we see here the elements. We already opened the wireshark, so we can see that there are some messages already here on the wireshark. So if we want, we can extract the logs of the near real-time rig in order to see some messages also here. Yes, so here we can see that near real-time rig is running. We can see that it loads the service models. It listens in this IP and in this port, and initializes the task manager with 2 threads and waits for the xApp to be connected. And now we can move to the second step. So step 1 was this. We deployed the 5G network with a near real-time rig. We saw some wireshark, and now we're going to connect the UE in the loop. So this is the step 2 now with the blue. We want, with a simple upgrade on the YAML file, to connect the UE and run a throughput test. So from the YAML file, this is the only difference now on the step 2 YAML, that we will add a terminal section for the UE in the YAML file. So here we specify the terminal, and the vendor will be open interface, 5G, standalone stack, terminal, preferred access. We specify the G0B that we want to connect, the core network that we want to connect. We give the IMCI and etc. The slices, the radio will be this band, the same band with G0B, and the readiness check. So the commands, in order to, it's the same command, CLI install network, and we use the step 2 YAML, which has only this difference that adds the UE in the loop. And then we're going to do the RTT test. So CLI install network step 2. So we can see that directly the NR RF simulator UE1 is connected to the network. Here on the status, we can wait for the UE to be connected, properly connected. We can see that all of the other are probably connected, and 1 out of 1, and yes, the status is healthy. Here we have the wireshark. And now that the UE is connected, we can see it is connected. We can run the RTT test. So in the RTT test, we specify UE1 and do the RT test to the gateway. So we see the ping. We see the ICMP message here, and now we can do filtering here. For example, we see with the NGAP that the UE is connected because we can see here, for example, PDU session resource setup request and response. We can also do, for example, in order to see one direction of the ping, we can see this ICMP messages, GTP protocol are coming, so the UE is already connected and the RT test is successful. So now we can move to the third step, which is to install now. Let's go back to the slides. So step 3, now we want to install the interactive xApp. So we have now the core network, we have the controllers, we have the UE on the loop, and we want to install the network. So the only difference now in this YAML file will be the edge section. We already have the flex rig, which is the near real-time rig. Now we want to add also the xApp, the slice CUI Go. It is written in Go, and it is a Go xApp that it's an interactive xApp that will show the PRB utilization, the throughput on the terminal. And again, we specify the model, some profiles. For example, we want to say that we will subscribe on the max service model and on the slice service model, and we give an interval of 10 milliseconds per indication message that is coming. So again, it is the same command. It's CLI install network step 3 YAML, and then we will run the xApp and the throughput tests. So here we install now the step 3. We see here the slice CUI Go, OAI SIM. The status will be 0 out of 1 because now we are gonna run the xApp. So let's now do this in another terminal on another tab. So here we can run the interactive xApp. Good. We see that it creates an interactive terminal. So there are 4 entities that are important here. There is the downlink throughput. Here in megabps, there is the PRB utilization in percentage, and there are 2 slices, slice 0 and slice idle. We will explain more about this later. So for now, it would be good to see the worksarc traces that we can see that there is, if we filter here to see the E2app protocol, we see that there are the RIC indication messages that are coming from the xApp, from the RIC to the xApp. We see the indication messages here. So the xApp is connected and receives the indication messages. And we can also see here, this is the flex RIC log, the near real-time logs. We can see that there is the E42 setup request received and response. So the E42 is the interface between the xApp and FlexRig, the near real-time rig. So we can see that the xApp is actually connected. And from the traces, we see that it receives the indication messages. So now we can do a throughput test. We will do for now the TCP using the TCP protocol. So the difference between these 2 plots now, as you can see from the plot on the left, you see that the PRB utilization is increased. It is 74%. The throughput here is 60 megabps. And so the difference between these 2 plots is that the plot on the left is on the run side. So it's the throughput that it is on the run because the xApp is connected to the run and calculates the throughput. And on the left, you can see the throughput on the application side using TCP traffic flow. So the difference will be that the throughput on the left will always be a bit higher than the throughput on the right, on the application level, because the throughput on the run includes some overheads, and also because maybe there are some retransmissions that the run does not understand that it's actually retransmissions because of the run perspective. It sees that it sends the packets, but on the application perspective, it sees that there are retransmissions. So maybe we will see, it's an interesting point to notice that there will be some difference between these 2 plots. Okay, so now Now that we have everything running, we can proceed to the step 4. So the step 4, now we want to run the Arabs, and we want to see the policies create the dynamic xApp, and we want to see the policies being enforced on the run. So here we have a policy sample. So we will run 2 Arabs. One Arab will be for targeting the PRB usage on the run, and another one will be for slicing. So this is a policy for targeting the PRB usage utilization. We can see that there are 2 important sections. It is the scope identifier here that you specify, for example, which slice you want to target, what UE you want to target, maybe several slices, a group of slices, maybe a group of UEs. And there is the policy statements, policy objectives, and you go load balancing objective and target PRB usage. So this is an ORAN compatible policy exactly from the specs that targets the load balancing PRB usage. So in this step now, as we can see, we will run 2 Arabs, the Arab max PRB utilization and the Arab slice enforce, and we will extract the logs from the flex policy dynamic sample. So this flex policy is the dynamic xApp that will be created, as we mentioned before, from Odin, from the non-real-time rig. Now, let's go to the first Arab will be for maximum PRB utilization. So let's prepare the ground. In this tab here, I will close the FlexRig logs, and I will be ready to open the flexible dynamic xApp policy that will enforce the policies. So we will see the logs there. And now let's open also here the Odin, the non-real-time controller logs. So here is the non-real-time rig waiting for the policy to come. And now we can start the Arab on this terminal right here. So the Arab is called maximum PRB utilization. And what we will try to do is to set a threshold on the PRB utilization to say, do not exceed this threshold on the run. This is the policy that you have to enforce. So I start the policy. The policy says maximum PRB utilization is 100%. So here we can see that we are fine because there is 70% PRB utilization. And now we can see that it is connected. We want to see immediately here that the flex policy dynamic xApp is being deployed on demand. And if we see the logs, we can see that it serves. So let's go back now. Now, this Arab here has sent the first policy, which is maximum, setting the threshold to 100%. So it's fine. The policy is fine. Now, a second policy is coming with 90%. So what we want to see here is that there are 2 slices. As long as the policy is fine, we can stay at the normal slice 0. But as long as the PRB threshold does not meet, we need to change line. And this is what happened right now, because we see the next policy is coming, setting 20% threshold. So we see that we change to the slice, to the idle slice, and we can see that the PRB now is reduced to 16%. Next policy is coming. The maximum PRB threshold is 90%. So we can go back to the first slice, to the normal slice, and we can see that the PRB utilization and the throughput is recovered. An interesting thing is that to see from the application throughput that there is also this pattern on the throughput here. It goes down, it comes up. So next policy, 20%, we need to change slides. We need to restrict the PRB utilization on the run. So it goes again 16%. So the policy is enforced. Next policy, 90, we recover here. So we see how a policy is coming from the Arab and is translated to a control action on the dynamic xApp. Now, the policy will be deleted. After this step, the policy will be deleted, and we want to see that also immediately the dynamic xApp is deleted. The flex policy, you can see here that the dynamic xApp is deleted. It's terminated. So now we can go to the second Arab. So the first Arab, the Arab that we just showed, was how we realize ORAN compatible Arab and what it can do. So it abstracts, it is run agnostic, it abstracts the user from knowing exactly what kind of control action it needs to do on the run. So instead of saying slicing, you can just say, I want to enforce this PRB threshold, and you can do it however you want to the non-RT rig. But now we want to show that there is space here to do whatever we want. We can explore, we can expand, we can extend the Arabs. And for example, the second Arab says that you can go, even if you want, you can go deeply down, more technically, you can specify the slices and do slice enforcement from the Arab level. So from the Arab level, now I will run the second Arab. This Arab directly talks run language and enforces slices. So we want to see that, again, the flex policy is the same xApp that will deploy the second policy. So this xApp can enforce multiple policies. So if we see the logs here, we'll see that it is fine. Here we see some feedback from the xApp. And now what we want to see is that we want to see that from the Arab, we can do slice enforcement between the slices. Now we create two static slices on the first policy. The second policy updates these slices because the first one specified a different capacity for the slices. Now we update the slices, and from now on, we want to do association of UE to a slice. Now we associate the UE to slice 0. We see that it is slice 0. The next one will associate the UE to slice 1. You can see associate UE to slice 1. Immediately it changes the slice, and we see the PRB utilization being reduced. And now we see this pattern. Then we associate the UE to slice 0. It goes back again to slice 0. And the PRB utilization also recovers. We can see also that it is from the application, from this plot here, the application pattern is similar, but an interesting thing to see here is that there is some delay, which is because of the TCP traffic flow, traffic control. So this is another interesting fact that we can notice between these two plots. So we see we associate the UE to slice 0, slice 1. So the main point here is that there is space for searching whatever use case we need. For example, maybe we need to go deep, maybe we need to go abstracted on the Arab level. So we can do the use case that we want. Here we saw two Arabs. The first Arab was the ORAN compatible Arab for doing PRB utilization. The second one was for slice enforcement, which is a custom Arab for our specific use case. So now we can move to the final step. The final step is these two commands. We need to remove the network, and then we need to do the Terraform destroy. So I will now remove the network, which is, I will use the step 3 YAML, which is the last one that includes everything. So CLI, remove network. And from the observe, we can see that everything is deleted, the elements are deleting. So now I will give back the monitor to my colleague, Alireza, and Alireza will show you what was the cost of using this, the GCP, the Google Cloud Platform, and how to destroy now the Terraform. So without further ado, Alireza, I give back the floor to you. I stop sharing.
Thank you. So as my colleague mentioned, now, because we are going to about to finish the first half and go to break, and the second part of the demo would be with our own cluster, internal cluster. As an example of on-premise cluster, I can safely delete my cluster on Google Cloud. So I just do Terraform destroy auto approve, and it would delete whatever resources that I was using to save the cost and money, like on Google Cloud. And if you want to see more details about the cost, if I come to here to, if I refresh, because now I want to see my cluster that I just created and deleted. This was the cluster. If I go to cost optimization, Okay, so this is what's showing the resource usage that it was actually incurred on the cluster, and this is what Google would charge you in your billing reports. Since the billing reports comes with a bit delay, like I think a few hours delay. What I can show you already is the reports from the other day that we run it for the full day. If I choose on Sunday, for example. Yes, so you see I was running for the cluster for the full day, the Sunday, the 24 hours. Now you see for 24 hours the total cost is 40 euros for the cluster itself and 16 euros for the API charges that was introduced. And in total, I would say roughly would be between 2 and 3 euros per hour if you use this on Google Cloud. Okay, so thank you. I think the next phase would be our short break for 5 minutes. And we would be still responding to your questions in the chat. So be with us for the second part of the demo, which would be about larger scale Open RAN. The second part of the demo would be about larger scale Open RAN, which we want to see Open Studio Observability for larger scale networks. So we developed a kind of a storyline behind what we want to do. Imagine there is a private vendor, private RAN, private 5G company that want to test and run their equipment on the 5G network. You could take example of, I don't know, for example, vehicles, like electric vehicles that they want to do. And they have, in south of France, they have like a development site that they want to test and develop their things, including like they have one GNOD in Nice area, one GNOD in Toulon, and one GNOD in Marseille. And they're connected to a single rig, which we call the rig south, with its own xApps or whatever. And there's a single core network in the south. We call it France South. And there are multiple UEs, one for Nice, Nostradamus, Van Gogh for Toulon, and Lawrence and Hemingway are connected to Marseille. This is the zone one, or the development zone of that imaginary vendor. And then you have zone 2, which is their production environment in Paris that they are testing now. They have multiple GNODs. You have one we put, just for the sake of being funny, we put one GNOD around each of the monuments in Paris. You have one in Eiffel, one in Pantheon, and one in Bastille, that they are making the South Paris network connected to the Paris South Core network with the corresponding UEs that you see in here. And you have the rig, they are connected all to the rig of Paris. Paris is the same as the GNODs in the north, which are in Louvre, Arc de Triomphe, and Palace Garnier, and Chaumont in here. So they're connected to the Paris North Core network, but they're connected to the same rig in Paris. So there is the same rig in Paris, and each of them have different number of UEs. I would show you the example of how that is done actually, and but the point that I want to make is that from this figure you would see that the GNODs that are close to each other, for example Louvre and Palace Garnier, they would use different bands and frequencies, thus to simulate the behavior. Okay, they shouldn't use the same band or frequency. Or the ones that are in the denser areas of the city, like Palace Garnier or Eiffel, they would use CUDU deployments that are more for denser areas of the network. And this would be our zone 2. So if I show you how this, the YAML description would look like, by the way, the Terraform is now finished and it is destroyed the whole network, and there would be no Google Cloud. And go to the description of the 2 networks. So this is the South network first. We would see that this is how we define the YAML files in general. So you could define your slices on the top. Here is just a simple slice as 00101. I would close it. you have one G node B which is in Nice with this particular network MBID, and in band 78 in this particular frequency in this TDD config pattern, and is going to connect to France South as a core network, and RIC South as a controller. And we are scheduling this to be on site 1. So site 1 is like our infrastructure site in around Nice. Then you have Marseille, which is going to do monolithic G node B. Again, you see the MBID is now similar configuration to Nice because it is far away from Nice, and connecting to the same core network and same RIC, but this time on site 2. So it is a different site. Then you have Toulon. Toulon is using the same site as Marseille because it is close enough. So it needs to use a different band and frequency and perhaps bandwidth, or TDD config is also different. So you could modify all of these options. Then this is the core network definition. We allow the core network to be in any of the sites. Any components of the core network could be distributed on any sites because they are not delay tolerant. And then this is the RIC definition that we are going to do, and the RIC is going to deploy on a specific site that we call it the edge site. Don't confuse the edge cloud. This is like the name of the site that we create. And the UEs, you see this is Hemingway. I saw in the chat that they asked us how we do actually define which access network or which core network they need to use. This is how. So for simulator mode, you need to give a preferred access because there is no signal quality, say which signal is stronger than which to connect. So we say this Hemingway needs to connect to Marseille with, and it needs to register itself to France South Zone 1. This registration is automatic, so it pushed the OAM would push to the database of the UE, so the database of the core network, so the UE is recognized at the core network, and it would do all the arrangement required to connect this to this particular G node B. The other UEs, we have Nostradamus that is connecting to Nice. We have Lawrence again, which is Marseille, and we have Van Gogh, which is connecting to Toulon. This is the first file, the first network file. And then you have the Paris one, which is more involved now. You have multiple key elements in here, 00102 and 00103, that are going to be assigned to the G node Bs. So then you have the G node B of Eiffel, which is going to be CUDU, as I mentioned, and it is filtering to use a specific key element. So it's on doing 00102 in the south and 00103 in the north. And similar to that case, you see there are now different sites and different RIC and core network in here compared to the network in the south. There's another G node B, the same key element, but with different configuration again. I don't go to the details of each. There's Bastille, the other one, Triomphe, you see. And they are carefully planned and designed to have different configuration when they are close to each other. There's another point to make, that is they have a definition called a scope for each of them, which defines where is the scope that they need to serve the service. So we give one name, a scope to each of them. This allows them, the UEs, to discover the right G node Bs and the core networks to connect to the right G node Bs. Also, you see this in this file, we don't define the NBID, because if you don't define the NBID, it allows, you're asking OEM to randomly generate. So when you're doing large scale networks, usually it is very difficult for you to maintain all the different things and IDs. So the options that are optional, the OEM would decide for you, including this NBID. We have Louvre, Chaumont. These are 7 G node Bs in here. And then you have the 2 core networks, the Paris South and the Paris North. And then we have, the interesting part is about the RIC part. Now we have the RIC of Paris, which is going to connect to all the scopes. And it is in the same site as the other one. So we are assuming that the compute site for the RIC is centralized for that particular operator that they are using. And then there's an interactive xApp that my colleague was going to use and show it, which is written in Python, this one. And this is for maintenance and control of the network. Is going to do a slice service model and KPM service model with an associated database, which this database is going to be this shared data layer that I'm deploying in here. In terms of UEs, I don't go again to the details. You have, as we saw, Season, Ledger, Russo, Picasso, Matisse, Metzinger, Delaunay, and Glaze. And then these are like the UEs that are connected to the same region. So my colleague was installing the network via Google Cloud, and with the CLI, you could install the network with CLI, or you could even use kubectl if you want. I want to use kubectl because I want to apply the two networks at the same time. It would create all the things. I have the SSH to my cluster master, so the commands are going there, because the cluster is downstairs at Eurocom. Now, if I do CLI observe, we would see it has created all the GNode Bs and the core networks. We need to wait a few seconds, like in general, less than 2 minutes to deploy this massive range of network. We wait for that. While we are waiting, I switch to my slides to progress faster. As I mentioned, we have the far edge site that is going to be connected to the vertical MVNO or MNO that they do SMO, including OEM, non-RTX, and ORAPs. You have the near RTX on the same site and zone, and then you have like near edge sites, which are the sites that I mentioned, compute site 1, 2, 3, and Trident that we are using in the file, and the different P elements. So this is just to give you another outlook of how that complex network is looking like. It would deploy more than 200 containers for doing this network, over 10 machines with 10 different RAN, GNode BSBC with 10 different RANs, and 12 UEs is going to be in action. And in total, there are 194 CPUs in our cluster. Not, of course, all of them are allocated for this setup, but just to know the scale. And the time would, would take less than 2 minutes to do the whole deployment. Okay, so I could scroll up and down and see what are the status of the different things. Okay. Let me check from here. Okay, I need to restart my OEM. So I lost my connection to it. Okay, so the OEM would manually, would automatically add the terminals to the network. So if I go to the terminal tab, I would see also that the UEs that are created with the corresponding IMSI and the kind that they're using and which access network they're going to connect to. There is the RAN tab. Getting the RAN tab, if I go and see, I would see the name of the RAN, what are the models that they're using for GNode B, CUDU, etc., what stack they're using. And you see there are the identities that are automatically generated and the cell that they're using. So if I go back to the elements, now everything is ready on this status column, as you see. Now I would stop on my side, and then I go to the slides because I want to give the floor to my colleague, which would focus more on xApp and ORAPs. But now we need to know how this is connected, the xApp, ORAP, and the ORAN stack, how it is, or OpenRAN in general, it is connected to this massive network style, is that OpenRAN actually enables the management and control of such large networks by utilizing different sets of range of ORAP, xApps, and ORAPs. And that is going to be the focus of the rest of the demo, to see these different xApps and ORAPs. We have already seen examples of ORAPs on Google Cloud. But now we want to dive deeper on how this spectrum of xApps and ORAPs would look like, which I would give the floor to my colleague, and she would start explaining slides. Thank you.
Okay. Thank you, Areza, for deploying the network. So there is a gap existing in the between the xApp and RApp in the OpenRAN ecosystem. which is not clearly defined in the current ORAN standard. So for different use case and for different role, like for the xApp developer or maintainer or the user of the app. And in the traditional ORAN, they only have two choice. One is xApp, another is app. And in this, so we propose this independent xApp lifecycle. In this independent xApp lifecycle, we break down the xApp into different options, xApp in here, to achieve this. To achieve xApp can be dynamically operated by the SMO and also accelerate the development speed of xApp, bridging the xApp and app seamlessly, and also enabling a smooth transition from RAN to the data. Like for the app perspective, the user of our app, they only need the data. They don't care about how to deploy the RAN in this case. So you can see this figure, there are 4 stages. We list the first 2 xApp, binary xApp and the containerized xApp. We focus on the xApp DevOps. And the third and fourth, integrated xApp and app, we focus on the data. And for this xApp DevOps in here, which is the same concept as the DevOps in the cloud native cycle. And we map the same concept to the data perspective between this integrated xApp and app. So this independent xApp lifecycle we propose in here, it's starting from the binary xApp to containerized xApp and to integrate xApp, and the end is app. So what's different between these 4 xApp in here? First is they are used by different people. Like the binary xApp is target for the vendor, the developer from the vendor, and the containerized xApp is target the maintainer from the operator, and the integrated xApp is target for the vertical user from application provider like the Netflix, and the end is the app is used by the data analysts or business intelligence from a stakeholder in here. And these 4 xApp we using in different usage scenario and different purpose. Binary xApp will target for the research and develop usage. Containerized xApp will target for testing and the measurement. Integrated xApp will target for production, and the end will target for analyze and optimize the whole infrastructure. And also the knowledge for the near real-time RIG API and the SMO API need the requirement for these 2 API are different for this 4 stage. Like if you are an xApp developer, you need to be really you have to have a lot of knowledge for the near real-time RIG API, then you can develop different functionality in your xApp to talk with RIG. However, if you are an app developer, you need to have more knowledge for the SMO API, because you need to know how to define your network intent, like the YAML file we show in previous slide. You need to show, you need to describe what kind of network you want to deploy, like how many E2 node, how many UE, and what kind of data you expect to collect. So if we move on to the first xApp, I'm gonna show the demo for the first xApp in here, which is if I'm a xApp developer, I will start to write a xApp in the beginning in here. So to develop a xApp, we need to using the near real-time RIG API in here provided by Flextree as an example. You need to at the right side is a simple example for the near real-time API provided by Flextree. First, you need to init the argument, and the second is you need to call the init function to start the xApp. Third is you need to get the number of E2 node connected to this RIG. And the third is you need to write your own callback function to process different service models information. And if you are using the KPN service model, you need to write another function to process the action definitions message to describe your data in the KPN service model. And the fifth one is you need to call this report service model API to send your subscription request to your specific service model. And the last one is when you want to stop your xApp, you need to remove the service model and stop your xApp API. So I'm gonna show you an example for this xApp in here. Save C BubbleRAN.c. So in this main file, you can see I call the init argument, init the xAPI, and get the number of E2 node. And after that, I will filter if the E2 node ID equal to 40, which means is the one we already deploy in the south of France, which is called Marseille in here in our network. If the node BID is 40, I will do the subscription request in here. So I save this file and I will compile this file by myself by enable the SQLite 3 xApp database. So now the xApp is compiled to then, because we need to connect the xApp to the rig. So there is already a rig in the cluster. I need to know what is the IP address for this rig by running this command to get the IP address. So we can run this CLI extract port system flex rig, and since I was giving the ID not BID at the south, so I need to connect to the south rig port E42AP. So this is the rig IP address in the south. Then I need to modify the configuration to give the proper IP address in the E42 port in here. This is the config. So in here, I need to give the IP address I got from CLI, and the port is 36422. And just take an example, since I'm enable the database, so I will name OpenRAN Studio. Okay, now we can run the xApp. So to run the xApp, you run your binary file, which you already compile, ran-c, and giving the configuration, you just modify. So from the log showing in the terminal, you can see the xApp is receiving the data from the rig itself. And if we want to do the test in here, you can run the CLI test for the UE, which is connect to the Marseille. Let me stop this exit. If the node ID. Okay. You can see the xApp is constantly receiving the data from the rig. And since I generated the traffic, so from the data receiving by the rig, you can see there is a data coming. And to show we actually collect the data in the xApp. I will open the database in here, the database temp. So there is one called OpenRAN Studio. This is the one I generate. And we can query this data. Select from main KPN indication measurement data info. So you run. Yes, you can see this is all the data collect in the xApp and writing in the SQLite database. There has a different measurement data. So this is the binary xApp. If you are a developer, then you need to writing your own xApp.c file, start from the beginning and knowing the API provided by the FlexRig, and compile all the things by yourself. Now we move on to the containerized xApp in here, which is provide to the maintainer to testing and measurement the network, to checking the connection, or to checking the new functionality developed by the developer. So in this stage, the action is interact with the network, and you don't need to have a full knowledge about the new real-time rig API, but you need to know just a basic knowledge, like you know what is the procedure talking between the xApp and the rig. So to start this Python interactive xApp, let me start this one. From the network, you can see there is already have a interactive xApp already deployed in our network in here, which is called interactive xApp zone 2, because this xApp has already containerized. So when AWS are deployed on the network, this xApp already deployed it in here too. So to go to this xApp, now I'm inside this containerized xApp. You can see in here, it will print which configuration you should use, which configuration generated by the system is this one, and what is the function provided by this interactive xApp. So to start this xApp in here, you can see what is, you need to give the path of configuration in here. And you don't need to modify the configuration in this stage because everything is automatically configured by the network, by the YAML file level. So all the IP address in this xApp.conf is automatically configured. You just need to give this as an input when you call the init function. So now the access already start and connected to the rig and print all the connected E2 node at the north of France in here. So you can see there has a CUDU and a 5G node B. And we gonna subscribe the service model to one of E2 node in here. And there is a function called print funcs usage. You can giving the function name in here to know what kind of input parameter you need to give for this function. Now I'm gonna do this subscribe. I need to give the index for the E2 node. For example, if I want to subscribe to this DU, the index is 1. And the service model name, I want to subscribe to slice. And the report time period, I want to report every second. And the last one is the action definition. If you are using KPN, you need to give the action definition, but we are using the customized service model in here, so there is no need for the action definition. So after I send the subscription, you can print the state. It's a print slice state. The first E2 node index 1. You can see, okay, there is no slice in this DU, but there is a 2 UE connected to this DU. So we're gonna do the throughput test in here for these two UE. And we will showing how to send the slice control message. Except send slice control. To send the slice control message, you need to give also the index, your slice action. In here, we will add a slice, two slices in here, and your slice configuration. For the slice configuration, in here, I will add capacity, NVS capacity as an example to NVS. So now I add the slice state to 1. You can see now there is a 2 slices in the system. And both of you are at the first slice, which only taken 70% of resource. And we have a function is called print slice config, which will show you what is the slice configuration you're gonna give. Like the configuration I gave to this slice control is this one. So you can see xApp slice. Oh. Yes, so the slice configuration I sent is exactly as the slice state report from the RAN in here. And from the result, you can see both of UE, the throughput are going down because they are sharing the same resource from the same slice. So now I gonna send another slice configuration, which is will associate the UE to another slice. Associate UE in here. And I will modify this configuration, which will specify the index of UE. In here, I want to this index of UE, which is 1, to the slice ID 2 in here. So I write this slice configuration, and I call the slice control message again. And this time, the slice action will be associate UE, and I give this slice configuration. Now, if I print the slice state, you can see the UE, the index 1 is going to the second slice. So we need to wait for the throughput. It will have some different later. So at the same time, we can check does there has any data coming to the database for this xApp. For this xApp, by default, it's using the MySQL database. So in here, we can do CLI CIC-N system. Cleaner system, MySQL database. Follow run --SQL. Oh. Now I'm in the database for this xApp, and trying to select the data from here, then slice schedule name ID slice horizon from slice order by safety. You can see there's a data coming, which is the current slice state. There are 2 slices, the slice ID 0 with 60% of resource, slice ID 2 with around 29% of resource in here. This is from a database, which is same as if you print the slice state in this interactive xApp. So let's check the throughput. You can see one of UE is going up to 96 megabit per second, one of UE is going down to around 30 megabit per second, which means the UE1 in here is the left one, and it only take around 30% of resource from the base station, and the first UE index 0 is the left one, is take 70% of resource from the base station. So this is the whole interactive xApp, and if you want to send the delete subscription and the stop this xApp, you just call xApp and it will left this interactive section. So if we're moving on to the integrated xApp in here, which is target for the data usage, in here I will pass the presentation to Elias to present stuff.
Thank you. So now we're going to talk about another thing. Now we're going to go closer to the data. So we will show an integrated xApp that is written in Python, and it can deploy a monitor. We are going to show from non-arteric how we will deploy a monitoring job. And this integrated xApp is now more programmable, and it can be used to analyze the data of the network. So from Odin, from the non-arteric, we're gonna send a different kind of the policies that we already saw from the Arabs. Now we're gonna deploy a monitoring job. As you can see, this monitoring job has specifies some tasks. And for example, we can target a specific G0 B or a list of specific G0 Bs. So for this demo, we saw that we target the zone 1, that from the massive network that we deployed earlier, we deploy this monitoring job to the zone 1, to the NIST G0 B, and we specify several metrics that we want to see, for example, PRB and SDU. And now we will see on our local cluster, here we have on the right part, we have the massive network. Here we have the Odin, the non-arteric, and we can see also the Odin controller here. And now we will apply one single monitoring job for targeting this network. So we see that the Odin reconciles and it dynamically creates the Flexmon Python xApp that will target specifically the NIS zone 1. So it goes to south zone 1, and specifically it targets the NIST G0 B in order to send data to the database. So now I will stop sharing and I will give to my colleague the monitor in order to show you how this Python xApp is working and what can you do for analyzing the data, reading the data, and obtaining statistics. So without further ado, I stop sharing now and I will give to Koa.
Hi everyone. Okay? So before we moving to the data part and how the monitoring xApp works, let us see what the data has been ingested inside. So this is the Grafana dashboard for the last 15 minutes. So the country code, the network code, the RAN ID, and the RNTI here. And this is the uplink aggregated physical resource block usage of this UE, and this is the downlink. So it is just slightly different. So that is the data is actually ingested. So let's move to what I want to demo. So okay. Okay, so let's first talk about the motivation for the flexible programmable monitoring xApp. So it all starts in 2020 when I was still a master's student doing an internship with a theoretical supervisor. So at that time, we want to do some machine learning tasks, and all we have in our hands were a data set called the Milano dataset, which was collected in 2011, which means 10 years earlier, by Telecom Italia. So the scope of the Milano dataset is very similar to the large-scale network that you have just seen deployed by my colleagues. So basically, it tries to collect data from multiple provinces of Italy and mapped the traffics this way. So, so to be honest, we didn't want to use the datasets for a very simple fact. That is because for machine learning, even for the same scenario, an optimal learner of pattern A will not translate to an optimal learner of pattern A prime, despite they are the same scenario. So it means that if all we can do is optimizing a learner for the Milano dataset, then it will not work in our scenario. It doesn't generate much insight and so on and so forth. So at a time, I really want to do a custom scenario data collection and do machine learning on top of that. And we are kind of aware of lots of works in the literature where people do large-scale data collection and real testbed data collection, but we couldn't follow their approach because most of them come from very large institute. Like from the left is Fraunhofer Focus, and on the right is Ericsson, Sweden. So we have to stick to that 2011 data set in 2020, but this Flexmon programmable xApp is the answer to the needs that we have back in 2020. So first of all, what is the goal of Flexmon? What is the architecture? So Flexmon had 3 goals. First, we really want you to get all the data you want with programmability in the simplest way. So why is this programmability needed? Because there are a certain metrics that you cannot recover by post-processing. For example, if you run your scenario under a certain configuration that is not inside the data, that is not inside the database, you cannot recover the whole scenario just by pre-processing. So having programmable pre-processing is very important. Also, we want you to be worry-free about the schema design. So in order to have a data lake, we need to ingest data from multiple sources, the RAN matrix, the energy matrix, the infrastructure matrix, and they need to design their own specific schema. So we want you to be worry-free about schema design. And also we want you to be worry-free about scaling as well. So we want the data lake to be reliable, to be able to work with other databases, and to be able to be bottomless. I mean, you can ingest as many data as you want. And finally, a data lake should be beyond Jupyter notebooks and go into production to support the 2 most important use cases of data. That is to monitor your network for reliability engineering and for streaming the data to a centralized controller. So to solve these goals, we basically make several key design decisions. The first design decision is that we adopt a very flexible data model called the tag-set data model. So in this data model, you can ingest without knowing the schema, and you can pre-process with very few assumptions. And on the right, we make several key design decisions as well. But the most important one is that we focus on a SQL, not NoSQL database, and that allows us to be distributed. And on top of that, we implement a custom triggers that based on each of the data coming in, we will normalize and we put data inside a database in the correct format. So this way, you do not have to worry about the schema and so on and so forth. Regarding the choice of PostgreSQL, we choose it because it has foreign data wrappers, FDW, that can work with any kinds of SQL database, and it can connect to AWS S3 for you to be bottomless. So this is the architecture. In the next demo, we will see that Prometheus will ingest infrastructure and energy matrix into this data lake, and we will have Rickman ingest RAN matrix into this data lake. So let's do it. So before I do the demo, I want to show you one thing. That is, we have completely get rid of Prometheus. It means that whatever you see next will be completely inside the database. We will not use Prometheus to work around the data lake concept. Everything you see is inside our database. So because we have disabled it, let's go back to the data we have yesterday. So here, let's just take an example query. So you can see the example query here is not SQL, it is PromQL. But our trigger translates the PromQL into SQL so they can query the SQL database. The reason why we showed you before that Prometheus is cute is because you might misunderstand it and we still keep Prometheus running. And for the same reason, you see this is the CPU usage for all pods in the Bastion Zone 2, networking I/O for Bastion Zone 2, and memory usage. It is the energy consumption in the last 24 hours in the whole CPU package in dynamic RAM, and also for the power. So if you click inside any of them, you will see PromQL is actually running, because writing these SQL queries is pretty complicated, especially when you use Grafana for network monitoring. That's the reason why that trigger would translate this PromQL into SQL queries. Okay, so that is the part on this one. We want to share on the data lake on PromQL. I'm going to share with you one more thing, but a very interesting thing. So if PromQL does this stuff, do we need SQL? Okay, so if you take the start here, you will see that despite PromQL is configured at a very small step 1, it can only have data in every 2 seconds. Despite the data is actually ingested every 10 milliseconds. So that's the reason why we still need a SQL language. So this is that same version for the PromQL, but in SQL language. So if you query it, let's wait. You see that this is actually the correct one. So it targets the same, like around 1,300 for the rate, but it is in a finer and more correct granularity. So we have shown you that we use PromQL for easy visualization, because network monitoring tasks needs to be very agile, and we use SQL for precise data analysis because machine learning task needs to be very precise. Now we will come to the most important selling point of Rickman. So for Rickman, we want to fulfill the promise that programmable monitoring is simple as copy and paste. So let's see what Rickman actually, what is the code of Rickman actually does. So here you will design for each of the service model and each of the E2 nodes what kind of matrix you want to ingest and at what interval. Then this is the runtime config. You just do it for performance reason. And then for pre-processing, for each of the data you specify above, you specify a chain of pre-processing function that will be applied. So where will these pre-processing function comes from? It comes from these two. So my visualization will be a one that extends this one that we import from our library of pre-processing with your own configuration here. And you can write your own preprocessor this way. So the reason Flexman is very flexible is because we choose to use Python. So the next question that comes to mind is that will Python be slow and affect your performance or not? The answer is no. So before we showing how fast Flexmon is, let's take a very popular website, Wikipedia. So Wikipedia can handle each data center around 3,000 requests per second. 3,000 requests per second. This is the live traffic of Wikipedia. And the 75th percentile of latency is around 240 milliseconds. What we promise to you is that we will ingest 4 times more in this amount with half of the latency that Wikipedia delivers to you. Why? Because for non-real-time control, you have 1 second control period. So your data ingestion, your data streaming has to be as fast as possible. And it would be nice if everything is under 100 milliseconds. So now let's start FlexRig and do large-scale monitoring. Okay, so we start different iteration. Okay, so now all 3 iterations is connected to FlexRig. Now for the database mode, I change it to true, and I will set it at 8 threads and 16 writing batch size. Okay, so then I will run it. You will specify your mapping remonetization here, and we run it. Let's run it for 10 seconds. So we start counting now. Okay, so within 10 seconds, you can see that we are ingesting on average 20,000 records per pusher. And we have 8 pusher, which means that we are ingesting 160,000 records in 10 seconds. Which means that we are ingesting 16,000 records per second. And the average head of line pre-processing time is around 100 milliseconds. So that is the end of my presentation for Flexmon. We hope Flexmon will be a tool that you will use for programmable and flexible monitoring at 4 times the scale of Wikipedia and half the latency of Wikipedia. Thank you.
Okay. Sorry, can you see my screen now?
Yeah.
Okay. Thank you for reminding. So this is the current ORAN architecture from the ORAN Alliance, and currently we are working for the audio. We are from the OSC Taiwan lab. We are focusing on the audio near artillery and also the OCU part. And we have some goals, like we already seen in the beginning, that in our lab we are trying to integrating many open sources from the OSC, OAI, and also from the commercial product, just like BubbleRAN and VRV. And for my part, I'm trying to integrate the BubbleRAN with the OSC modules. So the challenge is for the integration part is how we can try to manage the open interface and the standardization, since the OAI and the OSC, they will have some different format data, and we need to try to sync the data from, for example, just like from the FlexRig and from the OSC audio. And the second one is how we can try to have the plug and play xApps, since the xApp is also handled by xApp will handled by different vendors. And for each vendors, they will also have the different parameters, and we need to adjust the parameters. And the importance is bring the plug and play functionalities in ORAN is to simplify the deployment and reduce the setup times and also the seamless integration. In the current implementation, we will try to integrate the we will try to integrate the FlexRig and the rig part and also the audio part. Which is the rig part is from the FlexRig inside the BubbleRAN, and also the audio part is from the OSC, from the another open sources. And this is the challenge. Another challenge is we need to create the E2AP module from the E2 node, which is in the OSC source code is haven't deployed yet, but our team already create the E2SM, E2AP, and the E2SM in the audio, and we try to connect it with the flex strip from the practice from the OAI before, and in the current state we will try to implement the flex strip inside the BubbleRAN connected to the OSC audio. For the step one, before we implement, we will try to implement the bare metal version interoperability that we already succeed for this part. We already have the flex strip in the bare metal and the OSC audio in the bare metal as well, and we will try to have the demo in here. So this is our implementation. We have 4 terminals in here. The first one is near artery, the flex rig. The second one is the xApp. The third one is the OSC stop, and the fourth one is the OSC audio. And we in this tutorial we try to start from the flex rig, audio, and also OSU. In this one, the flex rig is already connected with the audio, and then we will try to start the xApp after this. So here is trying to, okay. Here the xApp is started, and the OSU stop is sending data, and the xApp can receiving the data from different slicing. For the current step, we already succeed to connect the flex rig or flex rig with the OSC audio. And for the second step, we are still trying to connect the the flex rig inside the BubbleRAN and also the OSC audio here. And from the flex rig will be outside BubbleRAN, but in the future we will try to have the xApps inside the BubbleRAN as well. And this is for the current state. For the current state, we can try. For this part, we are cooperate with Eurocom, with the BubbleRAN team to connect, and we are in this video. This is the BubbleRAN. This is the xApps, the bare metal xApps. This is the flex rig inside the BubbleRAN. This is the OSC audio, and this is the OSC OSU stop. As we can see, the audio can connect it with the flex rig in here, and but for the current state, the xApps still cannot connect properly. There is still some bugs that we are trying to discover and try to fixing in here. So in here, if you can see, when the xApps try to connect, there will be some problem, but we are still trying to figure it out, and we'll have some release in the future. In the future for this part. Yes, that's from me, and going back, giving back to Professor Navid. Thank you.
Thank you very much, everyone, for joining us for today. I just want to remind the agenda that we had today that we covered was the first part was OpenRAN Studio deployment on Google Kubernetes engine. So that was the first part we actually demonstrated. And the second part was deployment of the scalable 5G OpenRAN on our private infrastructure. We saw a bunch of topics ranging from xApp lifecycle, interactive xApp, observability, and the guest demo, which we are working to create interoperability of BubbleRAN with the OSC modules to make it also this full automation and at a scale. And also you see the presenters. I would like personally to thank all of the speakers for their support to make this event happen. Towards that, I have one slide on conclusion. So essentially we designed OpenRAN mini series as a forum to share the knowledge and foster the collaboration between the academia and the industry. And we would like really that you also participate actively into this collaboration and this sharing of knowledge in different ways that we could actually elaborate later. We would also value your feedback. So we will send to you a questionnaire which actually help us to improve the quality, the format, and the content of this upcoming series, probably organizing more panels, more discussions from the audience to that end. And I want to just remind you that this OpenRAN Studio platform, we designed it because our problem as a researchers at the beginning also was to have a platform that is flexible enough and provides the end-to-end connectivity from user to the internet and from the xApp to the RAN, so that we could actually carry out our research, create proof of concept. And OpenRAN Studio is actually designed for that purpose, to empower communities and organizations to accelerate the adoption of the modern technologies. So OpenRAN, cloud native, are part of the modern technologies, together with the AI ML-based data processing. We would like also use this platform as a ground to prove the outcome of the research and the teaching, to make this reproducible result every time that you are running, at least from the OpenRAN Studio perspective in a controlled laboratory environment. The way it is designed, we wanted this to be fully affordable and accessible means for education and the research, and that is what you saw in the map of the adoption, that actually this is getting highly adopted by many R&D centers and the university. And I really believe that this platform opens up possibilities and dimension for multidisciplinary research, because we are combining different domains here together: the cloud domain, the IT domain, 5G domain, OpenRAN domain, and the data science domain, all together, which we believe that this could actually pave the way towards multidisciplinary research. With that, I will let the floor to the Q&A session, right? I put here the LinkedIn and the YouTube account of BubbleRAN in case you want to have more information and get previous videos from the episode 01. This is also the link, direct link to the OpenRAN Studio product, that if you want more information, you can go there. Without any further comment, I would like to open the floor for the questions from the audience. I know that many audience are already left, but we still have 60% connected. So please feel free to unmute yourself and ask us your questions. We would be very much keen into having your questions. Maybe Kwa. Yes.
Okay, I'll take the chance to make a very basic question that comes out of my low knowledge of all this tool chain, if I can call it like that. This is Nikos from CTC. So if I understand it well, you are leveraging FlexRig that has implemented given service models and also have some custom service models. And we can have xApps, let's say, requesting data that are coming from the RAN. So from the other side, from the side of the RAN, let's take the RAN of the OpenAir interface, for example, which is the native solution included in the BubbleRAN. Are there agents developed there to return all these requests for data, or they are returning part of this? They are not implementing, let's say, all the requests for the complete service models until now. This is my very basic question, and I apologize if it is very naive.
Could you repeat the last part of the question, please? Because if I understood correctly, are you asking that if there is an agent in OI code that is setting the metrics, is that true?
So the xApp, let's say, requests some, let's say, metrics, but on the other side, on the RAN side, at the DU level or CU level, there must be some agent to collect this data and return it to the xApp, right? So for a given service model, let's say the KPM or the RC, this agent implements all the different type of metric collection for OpenAir interface.
So we have two types of agents in Flexic. One agent is that the agent that is integrated inside the source code. In case of OI or SRS, that is the case. That the part of the E2 agent code of Flexic, it is merged into the source code of OI and SRS, and it is reading the variables from the source code and sending the values to the xApp. There is also the other option of E2 proxy agent that we're using. If E2 proxy agent enables you to connect to non-conventional, say, interfaces, say, such as WebSocket or REST API or any other traditional model like Firebase to read the metrics from that. So if it is possible, in case of open source or in case of full adoption, we have also some vendors that are trying to fully adopt Flexic code, agent code into their source code. Then that data is natively read from the variables inside the code and then pushed to the xApp. In case of proxy agent, like if we don't want to fully integrate, then it uses the APIs of the RAN itself, whether it is WebSocket, whether it is REST API, file, whatever, to read those metrics and send to xApp again. The extent of this metrics would be limited to the service model that you have already onboarded in your agent, which in this case comes with the diamond libraries that Flexic it is processing. So as long as you have the service model support in the agent, in the bridge, and in the xApp, they could communicate and share the data and send the control messages as well.
So Nikos, to completely summarize, it depends on the service model and the RAN function. If the service model and RAN function implements those metrics or those statistics, then they will be available on the level of xApp by simply subscribing to that specific service model, whether it is custom or specified. So if, for instance, you have a need, you want a given metric, but it is not available, that means that, for instance, it needs that a given service model, you want a metric in a MAC layer that is not available, but you need, then that service model for the MAC needs to be extended. Or alternatively, for instance, the KPM service model could be extended to support that specific MAC statistics. But all of the RAN entities, CUDU, they have a dedicated agent that connects to the rig.
Okay, that's very helpful there. The answer. Thank you very much.
I should also include in the answer that based on code and what Paul showed to us, those pre-processing functions that you have in the programmable monitoring, those could generate second-level metrics, like the metrics that are built on top of other metrics. So if you want to do, for example, if you show PR utilization, it's not a direct metric that we get from OI, but we build it from the MAC statistics that are coming. So that means that not necessarily every metric needs to be merged into OI core and update agent, read service model, all this stuff. But you could also have them as the programmable monitoring approach that we have, especially if there are secondary level metrics that are made by composition of model metrics or by averaging them over the time. These type of metrics, this is code expertise, and that is what he's doing with the pre-processing functions.
And just one final point, because we are short of time, I only show to you the writing to the database part in streaming mode, which means we do not write to database, we just forward to the controller. Then the latency is 15 milliseconds, so it is very fast, suitable for near real-time control.
Right, thanks. Any other questions from the audience? We have still some time. So I will be compiling all the questions that we have on the chat, plus this video that we are gonna upload to the YouTube. So I will be sharing with you all the questions that have been asked in the chat, plus the video, in case some of the questions might also interest you that has been asked from the audience. I think with that, we can close the sessions if there is no other comments. Okay, so thank you very much to everyone for participation. We would like to see you for the upcoming sessions, and bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you. Bye-bye.
Bye.